Hello everyone, thank you for joining us today. My name is Abby and I am a Project and Administrator Coordinator at 2H Offshore. I want to welcome you all to our webinar today entitled Exploring Efficient Design for Jacket Platform Conductors. Before we get started, I would like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon by email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we will go through as many questions as we can, but if you have further questions, please feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Mark Hanning. Mark is a senior engineer at 2H with 7 years of specialist engineering experience in design, analysis and delivery of offshore platforms and riser systems. He has worked on projects primarily in the Northwest Shelf, Gulf of Mexico and North Sea, and is currently responsible for managing the design, fabrication and assisting in installation of a top tension riser project in the North Sea out of Perth, Australia. And with that, I will pass over to Mark to get us started.
Thanks, Abby, for that very warm introduction. Yeah, really excited to be here today and speaking about this topic. And I hope everybody on the call today, and I guess hearing this later, finds it useful. So just a quick overview of what we're going to be talking about today. So I'm really going to be focusing on how can we adopt a more cost-effective approach in design, specifically of jacket platform conductors. And ultimately what we want to do here is we want to reduce the total cost of ownership. So it's not just about putting a lot of effort in at the front of the design, but it's also about reaping the rewards of that towards the end. So we're trying to think about how can we use an efficient design approach and bound the problem? What can we do to enable robustness to accommodate future design changes or future changes down the road? And how can we kind of define those long lead items at an early stage? So I'm just going to be covering 4 things today. So firstly, just an overview of shallow water concepts, trying to understand the system response a little bit better so we can kind of guide that approach. How do we conduct early stage design, and a case study to kind of complete the picture. So first off, just a few of the concepts that we're going to be covering. So on the left-hand side here, we've got a jacket platform, and we can kind of see the jacket system in yellow, and conductors are running through this in grey. Next along the line, we've got a jack-up drilling rig. That can also be used as a production rig as well, where we've got these classic jack-up legs, and they're really a shallow water concept. We've got a derrick off to the side here. You can see the derrick in both of these ones here. And on the right-hand side here, we've got a minimum facilities platform. So this is where you get the conductors essentially acting as that structural member that's holding on the top sides. So understanding the system response. So like, why is this important? So platform conductors have a safety critical function because they're often the structural barrier that is holding the weld together. So the system response is the main factor in that sort of structural integrity. So the question really is, how do we design it in an efficient manner at an early stage? So when we don't have that much data, we don't have too much information, how can we do that at an early stage? So one of the key things here is we really need to understand the factors that control the stress response. So how do the well loads, so types of operations, types of configurations really affect that loading, and how do the lateral supports and the thought of lateral supports kind of interface in with all of that understanding? So I guess the first thing is you really got to understand what's the cost. What's the cost of failure? What's the cost of doing it wrong? What's the cost of it having a problem? So on the left-hand side here, we've got cost on the y-axis here, and on the bottom we've got a couple of examples. So loss of centralization, often, you know, down the line that might just be an engineering assessment and some schedule repairs that might cost an operator, you know, $50,000 or 50,000 pounds, as it's kind of shown here. Next along the line is maybe something worse where we have a connector failure. So we're seeing some leaks from a connector. That might cause a well shut-in, engineering assessments and emergency repairs. So that's going to cost you $500,000. Not really looking forward to that. And really down the real bad side is our well collapse. So, you know, facilities shut in, Yeah, really losing a lot of money there, a lot of time as well, and a lot of effort. And these sort of things can be done in a retrofit way. Like there's some examples here that I've put for that with that 2H themselves have done. Just showing the top one here. So like a guide installation, a centralizer replacement, and a conductor sleeve. And these are all retrofit solutions once these sort of things happen. And often the case is because they're just not, the problems that have occurred just aren't thought of at the design stage. So just understanding the system response here. So I've got four different types of, I guess, wellhead systems or well configuration. So we've got our bars on the left-hand side, which is tension in green and compression in blue. So for a hybrid well system, so maybe it's sitting on the conductor. I've got some nice images here which kind of show what happens. So we've got our production coming from the bottom, and we can see that change where it kind of goes into compression and then into lift up of the wellhead. But both strings are essentially in compression. So the second one here, we've got a lock system. So casing and conductor are locked together. So what happens there? So again, production, case, both in compression. But now because they're locked together, they don't rise as much, and also the conductor is kind of pulled and alleviates some level of the compression that's seen within that string. Maybe a different system here is maybe you have a locked wellhead at the top, but you have an MLS down the bottom. So mudline suspension system here. So we're hanging off a portion of the casing towards the bottom of the string. Again, very similar, but now maybe the rise isn't as large because we're kind of separating the subsea casing and the downhole casing. So, and both systems now going into maybe a bit less compression is kind of seen in, tension is seen in the conductor. And the final one here I've got is injection. So what happens when we're gas injecting? What happens with the profile then? So we're putting in something cold into the well, and we're seeing a bit more of a change into both strings going into compression. So that's kind of the loading systems that are occurring, some of the options that are that could be available at the design stage. So the next one is the axial support. So just a simple, let's say, no guides, just something sitting in the water. You maybe have some tension to keep the response good. Okay, so we've got very little change there. Again, if we get rid of this kind of tensioning system, we're kind of in a compression setting here. But when those loadings starting to occur, now we're starting to get this kind of displacement option, this displacement here caused by wave loading. But what happens now if we maybe put some guides in? So same system here, maybe a bit of a heavier load, and we're getting a little bit more kind of compression, different shape in that sort of sense. The final one here, wanted to highlight was centralization. So what happens when we kind of centralize things up a little bit? So you might have this kind of shape in terms of the displacement of the conductor if you've got these three guides for this kind of gap spacing. So maybe this is kind of a tight, rigid spacing. Whereas if we kind of have bigger gaps, we're going to have a bit of a different type of shape where the conductor is kind of bending a little bit more throughout. Oops, sorry. So it kind of looks like this. So in terms of definition, like what are we doing or what are we getting out from this understanding the system response? So in terms of inputs, we have different types of operations. So I've highlighted a few there: production, gas injection. Then you have the platform. So the platform itself may move based on what the water depth is as well. You have wave loading, current loading, and even soil strength. All those environmental factors play into kind of the inputs. So what are the outputs that we're kind of looking for in terms of designing? So we're looking for the casing configuration. Does the surface equipment need to be supported through drilling operations or production operations? How big do the gaps have to be? So what level of centralization is needed? How big can those spans be between each of those guides is an output. And obviously conductor size and grade, very important, and the setting depth, so the length of that conductor. And maybe whether you need to even do any marine growth cleaning. So what type of cleaning needs to be involved to make sure that when things grow on your conductor, that's not influencing the kind of the loading onto the conductor. So in order to do that, we've got three things that we need to kind of design for. First one is well loads. I've already kind of touched on it a little bit. So that can be the well loads through construction and how the conductor and casing share those loadings. The second is looking at the strength and stability. So we're essentially looking to enable that the resistance to overstress and buckling. And how strong do my connectors also need to be in terms of bending and tension capacity and compression capacity to withstand the loading. And finally, we have fatigue loading, so that high cycle loading, so establishing what are the kind of key components along the system, whether we have driving fatigue, wave fatigue, and VOV fatigue, they're all components of that fatigue loading. And in terms of application, so if we have all these outputs, what are they enabling for us to kind of define? So I think conductor size and grade and conductor length are pretty obvious. Conductor pipe and connectors can be kind of starting to spec out. The casing configuration, so if we understand the well loads, we can start understanding what the implications are for mudline suspension systems, whether we need what type of tieback connector or quick connector we might want to use at mudline if that was an option for us, and maybe potentially what type of wellheads we're kind of looking at. Marine growth cleaning requirements. So what kind of coating spec do we need to kind of limit, or we don't care about too much if it's not a problem. Some of the jacket limitations, if we can kind of identify those span lengths, type of gaps that are guides, so type of centralizers, so whether those are inserts, whether they can just be steel, whether they need to be polymers, and some other etc. Centralizers there, and for surface equipment sports, whether we have any MODU limitations. So we're kind of looking at speccing essentially this whole system here on the side. This is just a conductor that's being drilled through on a platform. So we can start speccing out or understanding what refinement can be made of that system. So potentially you might have this sort of load case matrix where you've got all these options, so you've got all these different operations so that you need to cater for, all these different type of well configurations that you might think of, all these guide configurations and environmentals. So you might have a lot of these kind of things that you want to play around with at the design stage to specify, and you need to do all these three analyses for each of them. So if you start adding those up or timesing them out to see if you wanted to cover every single one of these load cases, it simply really isn't efficient to cover all the variables of environment, all the variables of operation, all the variables of well and guides, and it's just too many. So how can we kind of simplify this down and make it easier to understand what we can potentially get out of the system? So I think one of the key things that we do here at 2H, and one of the things that's I think we've really moved forward with this sort of space, is combined simulation solutions. So looking at it, specialist parts of it so we can capture a really complex scenario, but be able to capture it as accurately as possible. So the way we do that is we can utilize different types of software for each of their capabilities. As we can understand those pieces of software, we can understand the inputs and outputs of each of them to kind of pair them together and pair the relevant data together. We can understand the impact and contribution, so it's not just a handshake between, let's say, the wells team to the conductors, to the structural team. So we can kind of understand the impact of our decision making at the wells design stage, and we can use each of those packages ourselves. So we're essentially combining all the loading mechanisms and revealing the whole picture in a better way. So we've got this kind of image here that shows some of the software packages we use. So we've got ANSYS, FlexCom, WellCat, and CasingWare. Today I'm really going to be focused on the bottom two here, WellCat and FlexCom. So we're looking at this kind of mirage of a more accurate wellhead and fatigue and conductor analysis, because we can understand the well loads that come out of WellCat, which is used to determine the loads of internal tubulars, and pairing that up to obviously with our FlexCom, which can do the stress analysis. So by doing that, we can kind of start to bound the problem based on understanding how those well loads affect the conductor. So we can kind of focus specifically on the operation and well configuration a little bit more. So we can understand how drilling completions, production, shut-in, injection, and the well configuration operations all pair up together to kind of define and bound the load case that we need to look at. So design flow. So when we start off, as I said, we start off on that well cat side. So we're starting off, I guess, with our most assumptions, with our well path ranges and our production ranges, and potentially well configuration ranges. And from there, we can go in and we can understand. So let's say from our image down below here, we might have two prospects that might be both oil wells, or one maybe is an injection well, and we can understand what are the well loads that are coming out of these two prospects, and how does that influence the conductor loads at the wellhead platform. We can take those loads from WellCat, put them into FlexCom, and understand where the highest compression loads are coming from, where the highest tension loads are coming from. And we can move on through and start to do our FlexCom analysis, which is our casing stability and buckling analysis and weight fatigue analysis, to really understand how that's going to influence the actual speccing of the system. So I've got a few, I guess, little images down the bottom here, which kind of show some of the things that come out of each of these particular design tasks. So for our stability and buckling analysis, we're really looking at critical spans and understanding that, and our guide gaps, and whether we need casing centralization of our internal casings. And then for our fatigue analysis, we've got the bottom down here, which is showing we're really kind of speccing out our connectors and confirming the size of our conductor and the length of our conductor. And we're moving from a most assumption side on our left-hand side to a more refined side on the right. And the final thing that we need to really take into account is this kind of loop, this flexibility loop of understanding that if things change on the left-hand side, how does that change the equipment that we've kind of spec'd on the right-hand side? So a summary of that. So first thing is we need to identify well load combinations, so operations and configurations. We bound the problem, we simplify the load cases to the most onerous compression and tension cases. Then through experience, we can understand and define the conductor size that's potentially required for the water depth, mid-ocean conditions, and well loads. We do our confirmation, so we do our strength and stability analysis to confirm the maximum span size and well configuration. And finally, we're doing fatigue analysis to confirm the connector and guide gap requirements. So we're essentially capturing all of those combining all those load mechanisms to really reveal the whole picture. So just going into a case study of how that potential process may work and may flow. So just looking at design of a platform jacket conductor for a new development. So this the one on the right here. So jacket, as I said before, in yellow, conductors in grey through the middle here. So the operations that we had to consider, or we might want to consider for this, is drilling. So drilling the well, early and late production. So you might have some variability in the amount of water that's coming through. So that affects the temperatures of that particular well. Shut-ins, so you can have ranges of different types of shut-ins that might be thought of for this particular, for the wells. So whether that's maybe a three-day shut-in, or a 1 hour shut-in, or a 7-day shut-in, having the flexibility, understanding that. And finally, gas injection. So whether we're re-injecting the gas, how does that affect things in terms of designing the conductor? And for the well configuration, there was the option to choose multiple mudline suspension systems. So whether that's hanging one casing off, 2 casing, 3 casing, how do we support the BOP, and what sort of size in terms of the surface tree that we're limiting ourselves to. So water depth in this particular application was 90 meters. 1,000 year HS 15 meters, and the median ambient HS at 1 meter. So this is 15 meters is applicable to our strength work, and the 1 meter is more applicable to understanding the fatigue response. So design flow here, so same thing again. So identifying the well combination, so the operations and well configurations that are possible. We're looking to bound the problem, so simplify the load case to the most onerous compression case and tension case, and then consider what a base case might be based on our understanding of, from designing previous systems. So I've got the same sort of color grade down here on the bottom, so tension in green, compression in blue, and different types of operations kind of ranked here on the left-hand side. So injection, completions, drilling, shut-in, early, late production and early production, and different types of supporting mechanisms. So just conductor supported, one casing maybe put on the mudline suspension, two casings on mudline suspension, and three casings. And you can kind of see by the color grading that I put in here, it's that we're expecting the compression case to be the worst for conductor supported with injection, and best if it's in early production and with most of our casings hung off on the mudline suspension system. So in order to really start off the process, we're looking at the most compressive case. So as base case, taking this first conductor supported case, and then potentially looking to confirm that that is definitely worse than our completion case, and also what's kind of the movement that we can make if we need to reduce the compression. So we're having a look at two casings put on the mudline suspension. So we get our casing loads from WellCat. So completions here just showed the axial load on the conductor here in tons and kips. So after completions, getting 760 tons, early production 173. So alleviating the conductor compression and almost going into tension. The shut-in condition essentially returning to compression, and then ejection we can see here is actually the worst in terms of the compression loading here. So we're kind of confirming the fact that this top right-hand corner with our conductors supported is going to be our worst case in terms of assessing the conductor. And so what happens if we just put two of those casings on the MLS, and we can see that kind of reduces that compression loading to 400 ton. So response-wise, so we're looking strength and stability here. So we're trying to confirm the maximum span sizes and the well configuration here. We've got two graphs on the left here. So just going to focus on this one in the middle first. So we've got elevation above mudline on the left-hand side. We've got our utilization of strength and stability. So how much buckling, how much overstress can this particular system take into account. We use bar and stall to do that, and we're looking for a utilization below 1. We've got the guides here shown, and what we can see here is if we're comparing MLS cases, so no MLS, we can see that the gas injection really is worse when that has with those compressive loads. So a utilization of almost up around 1.9. And the reason why we're seeing this little spike here is because for those cases, we've got corrosion that we need to consider, because that's the development of corrosion over the life. So we need to really, with these results, we need to consider an MLS to kind of reduce the compressive loading on the conductor. So the next graph along here, the second one here, is showing the difference between having a no MLS and having two casings hung off the MLS. And we can see here for that same gas injection case, we can get our utilization below 1 here. So that meets the target that we're looking for. So what about, I guess, playing with a couple of these things, like how close are we actually to optimizing the system with the present understanding? We can play around with the span length, so span lengths dropping it down to as low as 20 meters or as big as 35 meters. And we can kind of see that we're pretty close with our base case thought process of it was at 30 meters, so pretty close to the utilization. And if we really wanted to, we could max it out to 35, but maybe allowing a little bit of movement down the line is a good thing. And the second point here I've got here is what about centralizing the internal casing? Because we have the function of them is also creating a level of force on the conductor itself. As you can kind of see this diagram here, which shows the conductor and the casing here. So conductor is in black and casing is in red. When these start to bend around, if they're centralized within the system, there's zero eccentricity is what we call it, which creates the least amount of internal moment. Whereas if there's no casing centralization, those internal forces are larger, and you can get internal forces that are bigger. So we have a case here that's showing centralization of the whole string. So this middle case, we get a utilization of 0.78. Whereas if we have no centralizers, which is what we previously showed on this left-hand side, we have a utilization of 0.9, so 98. So there's a little bit of a change, and that allows a bit of flexibility down the line as well. So in terms of the wave fatigue response, so what we're looking for here is to confirm the connector and guide cap requirements. So considering here the long-term gas injection operations and the output that we got from the previous study, which was 2 casings hung off the MLS, this time we're just going to consider a standard radial gap, so 1/2 inch is pretty standard within the industry. And what we can see in terms of the response here is that we get our a hotspot here in this splash zone area where we've got our most corrosion. For this particular study, we're looking at a 200-year target life, so that's 20 years of production of gas injection or whatever, times a factor of safety of 10. And the graph here shows fatigue lives on the bottom and different values of stress concentration factors, which are representative of, I guess, different types of connectors. And we can see that we need a stress concentration factor of around 3.5 to kind of meet that if we wanted to specify it loosely, or if we wanted to specify it and space it out a little bit more accurately, maybe down the line, maybe an installer might think about just placing a connector away from this hotspot location, which is around 92 to 97 meters. So in summary, just want to go through, this is just an efficient and effective design approach to kind of bound the problem. So we've gone from, I guess I presented 200 to 300 low cases if we really wanted to consider every single potential possibility, to bounding it up to the most onerous cases to make the design process more efficient. And the way we can do that is by having a good understanding of the system, which can identify all the critical areas. Which the second point there is we're looking at making the analysis as realistic as possible and including all the loading mechanisms, from having a really good handshake and understanding between the well loads, which come from WellCat, and the stress analysis, which is done in FlexCom. And that kind of allows for an early stage design. It allows you to start specifying long lead items, start specifying equipment requirements, and starting to engage with vendors. And consideration of those at the design stage can also, obviously, you can avoid costly intervention activities down the line, such as repairs and shutdowns. Cool. Thanks for your time today, everybody. If you've got any questions, feel free to fire them at Abby and I'll be happy to answer them.
Great, thank you, Mark. We've already got some questions coming in from our audience, so I will go ahead and get started. The first one is, how do we start an early stage design process with no data?
Yeah, I guess it's an annoying question, but it's a realistic question. Often you want to maybe start this process as early as you can, but data is the hardest thing to find. I think one of the great things about coming to an experienced designer like ourselves is we often have offset design that we can use and understand. So something like soil data, metocean data can be thought of as analogous in certain particular areas of the world. So I think that's a great thing to take if you don't have the data available to you to start the design process, to enable starting the design process as early as possible.
Okay, thank you. So another one is, through one of your study reports, I encountered the concept fatigue due to thermal loads. Is this a real concern in the industry?
I think it is a real concern. It's definitely something that we're seeing more and more. It depends heavily on, specifically, I would say, the soil types that are around in the area. I can give a good example, I guess, living in Perth, which once was underwater, Australia, a lot of the soil around here is called calcareous. Calcareous soil is essentially old shells that have been smashed down. And one of the poor performances of calcareous soil is that when it's first engaged with loading, it's really strong. It's really stiff. But once it starts shearing, the mechanism of that strength really reduces quite quickly. Like I guess if you had shells in your hand and you started squashing them around, they just essentially become um, sand. So if you think about that mechanism, when you had all this air within the original case, and then all of a sudden it goes down into sand, it's gonna lose a lot of its strength. So that's the initial kind of thought process, I think, with calcareous soil. And then how does that connect with thermal degradation or thermal cycling? Is that when you heat up the conductor, it's gonna rise up, as kind of what we showed with those graphics earlier, and then when you cool it down, it's gonna go back down. So it's gonna have some sort of motion or mobilization. So that process of degrading the shells up is going to occur, and that's where you can see that kind of degradation of the soil that's occurring. And so I think it's definitely a problem. Whether we will see it being as big of a problem as what it's been identified at the moment, I think only time will tell. But thinking about it early and engaging it in early stage will enable it to be thought of now instead of in 20 years' time, when I guess everything's subsiding a little bit and that's not maybe what you wanted or what you thought about.
Great, thanks, Mark. Another one that came in was you use the terms SCF and
Yeah.
SAF. Are these terms the same?
No, they're actually not the same. So they're interchangeable, but they're slightly different. So stress concentration factor, which is an SCF, and stress amplification factor is an SAF. So stress concentration factor is typically a design curve, or a design name, which says that stress will be concentrated due to geometry differences, and it will be the same independent of the stress that you apply. Which is the case of how we consider it in design. So often we use that stress concentration factor in design. Whereas stress amplification, which is typically associated with connectors, says that there's an amplification due to the stress that is applied. So that profile is maybe not the same for every single stress. So stress amplification is when you have a stress and you have a particular fatigue performance, and that may change through the stress range. Now, that's why they use stress amplification typically for connectors, where they have different performances at different stress levels. Now, that's what we consider in design is, I guess, SCFs and SA, and we try to infer that an SAF will be similar in real life. So I hope that kind of answers that kind of question. It's a little bit complicated and can be a little bit messy. But often in design, you're really using stress concentration factors because you're not changing how you interpret the stresses that are coming from the analysis into different fatigue lives for different stress ranges.
Okay, thanks, Mark. Another one that came in, how do we consider MLS in FE modelling?
So I guess the easiest way to think of an MLS is just something that engages at the seaboard and creates a boundary condition. So that's the way we have used it. There's different types of MLS, so that's also something to be aware of. It's not always a hard and fast rule, so it's really good to be able to engage with the operator or the vendor of that particular MLS, but typically speaking, we just use a boundary condition in FEA.
Okay, thanks, Mark. The case study shown was in 90 metres of water. What is the maximum water depth this process may be applied to?
So I think with shallow water, which is all the concepts that I was kind of talking about, we can kind of see jackets or platforms being used to around, really extended out to maybe 120 to 130 meters. So I would say that's where jacket platforms or platforms in general and jackups in general are looking at kind of capping that range out at about that depth.
Okay. Who typically owns the design of platform conductors?
Yeah, that's a topical question. Um, it's it it should be the Wells team, but often it is the structures team. So there's sometimes one of the difficulties of especially integrity for a conductor is that it gets handballed to the Wells team and handballed to the structures team, and then handballed back to the Wells team. So it can often be something that's missed. It should really ultimately be part of the weld design, as kind of I've highlighted here, is that the key handshake is from WellCat to Flexcom, so understanding those weld loads. But that's essentially where you need a kind of a multifaceted team there where they are communicating effectively between the welds and structures team.
Okay, I think we've got time for one more. So, final question. Looking to the future, how can this approach be sharpened even further?
That's a good question as well. I would say, I mean, really, we've been designing conductors for years now. It's not something awfully new. You know, shallow water, typically speaking, it has been the first endeavor of most oil fields. So, making this, I guess, this is a bit of a movement towards making an efficient design process. So we're not looking at all those cases that we need to. The next step along the line will be then putting that into kind of the machine learning space and trying to understand it even quicker. So being able to look at multiple load cases and finding out solutions to problems at an even rapider rate. So I'd say that's the next step in terms of sharpening the pencil.
Great, thanks, Mark, for all the information on the topic. Unfortunately, that is all the time we have for today. But as we mentioned earlier, if we didn't get to your question, or if you would like to continue this discussion, please contact Mark directly using the details provided here. Thank you to our audience for your time and participation. We hope you all find this useful and will join us for more webinars in this series happening once a month. Check out the 2H website and LinkedIn for more details to sign up. Again, please look out for the recording of the webinar in your email in the next 24 hours, and we hope you enjoy the rest of your day.